Hi, this is your video for section 8.1 about the sampling distribution of a mean. So what we're talking about is the sampling distribution of the mean, and it is the distribution of sample means with all samples having the same sample size n taken from the same population. Sample means target the value of the population mean. That is, the mean or expected value of the sample means is equal to the population mean. So suppose that a simple random sample of size n is drawn from a large population with mean, mu, and standard deviation sigma. The sampling distribution of x bar, which is the sample mean, will have a mean that's equal to the original population mean mu. Notice the notation here. We have the symbol for the mean, which is mu, with a subscript of the sample mean x bar. The standard deviation of this distribution will be the original population standard deviation sigma divided by the square root of the sample size. Again, our notation has sigma, which is the standard deviation symbol, with a subscript of x bar, which is the sample mean. So this means it's the standard deviation of the sample means. And the standard deviation of the sample means is also called the standard error of the mean. And you'll see that in some places, sometimes in your MyMathLab homework or even in StatCrunch. Now the shape of the distribution for the sample means depends on what the original population looks like. If the original population is normally distributed, then the distribution of the sample mean x bar is automatically normally distributed. So if the original population has a normal distribution, then so does the sample means. If the original population was not normally distributed, then we don't necessarily have a normal distribution for the sample means, but it gets to be more like a normal distribution as we increase the sample size. Here's an example of sampling from a population that's not normal. So this table and the histogram show the probability distribution for rolling a fair die. So here are all of our possible outcomes for the face on the die that comes up, and each one has a relative frequency or a probability of 1/6. And here's what our histogram looks like. So this is definitely not a normal distribution. It's what we call a uniform distribution because every value has the same probability. So if we found the mean and standard deviation for this probability distribution, the mean would be 3.5 and the standard deviation would be 1.708. And again, this is not a normal distribution. So according to our central limit theorem, as n, the sample size, increases, the shape of the sampling distribution of x bar will become more and more like a normal distribution. And we can see this effect by simulating 200 simple random samples of our die rolls with samples of size n equals 4 and n equals 10 and n equals 30. So here's a simulation of 200 samples of size 4. If we take all of those samples and find the sample mean for each one, and again this is on our die rolls, so we're finding the sample mean of the 200 die rolls. And the distribution of the sample means looks like this. So it's not exactly like a normal distribution because we have more values over here and it's not quite symmetric. Now if we go up to samples of size n equals 10 and do the same thing, then we have something that looks a little bit more like a normal distribution. It has higher frequencies in the middle and the frequencies go down on each side. If we go up to samples of size n equals 30 and do 200 of those and find the sample mean for each one, then we really do have something that looks quite a bit like a normal distribution. It's not exactly symmetric, but it's much closer than our picture was for samples of size 4. Now to find probabilities for sample means, we're going to be starting with a population that has a mean, mu, and a standard deviation, sigma. And we'll know what both of these are. Using those, we're going to find the mean and standard deviation for the sampling distribution, for the distribution of the sample means, using these formulas. So the mean that we'll use is exactly the same as the one we had for the population. For the standard deviation, we have to take our original population standard deviation, sigma, and divide it by the square root of the sample size. And then using this mean and this standard deviation, we'll find our probabilities using the same methods we did in Chapter 7 for a normal distribution. So here's an example. Let's assume that men's weights are normally distributed with a mean of 191 pounds and a standard deviation of 30 pounds. So here's a typical problem we would have had in Chapter 7. Find the probability that if an individual man is randomly selected, his weight is less than 176 pounds. The key here is that we're talking about an individual, not a sample. Since this is a probability for an individual, we just use the mean and the standard deviation from the original population. So here's our picture of our normal distribution. This is our mean and our standard deviation. So we can plot our mean here in the middle, and this is going down one standard deviation. That kind of gives us an idea of where our value of 176 is going to fall. And since we want the probability that the weight is less than 176, we're shading from there to the left. So what we're finding here is the probability that x is less than 176. On our calculator, we'd use normal CDF. We're using a large negative number down at this end, and then our 176 for our upper bound, and our mean and standard deviation. So this probability turns out to be 0.3085, or about 31%. Now here's a little bit different problem. We want to find the probability that for a sample of 16 randomly selected men, the mean weight is less than 176 pounds. So instead of talking about an individual man's weight, we're talking about the average weight for this sample of 16 men. Since we're talking about a probability for a sample mean, we still use the population mean as our mean, but for the standard deviation, we have to use that formula and divide our original population standard deviation by the square root of the sample size. So our standard deviation for this one is 7.5 instead of 30 that we used in the last problem. So here's our picture of our normal distribution. Here's our mean and the standard deviation that we're going to use. So here's our mean in the middle, and this is going down one standard deviation. That puts the 176 actually down 2 standard deviations. And we're shading to the left again. So here's our probability, and notice the difference in the notation. This is saying the probability that x bar is less than 176 instead of just x. We're still using normal CDF with our large negative number as our lower bound, 176 as our upper bound, 191 as our mean, and now we have the standard deviation of 7.5. This probability is 0.0228. So to compare the two normal distributions that we just looked at, here was our original one with our mean of 191 and our standard deviation of 30. And here was the distribution for our sample means, which had a mean of 191 but a standard deviation of 7.5. So notice the difference if these are graphed on the same scale on the horizontal axis, how much more condensed this one is. The values are much closer to the 191 than they were for just the individuals. And notice in this one, our 176 fell not even 1 standard deviation below the mean, and in this one it's 2 standard deviations below the mean. And then if we compare our probabilities for the individual to be less than 176 pounds, it was about 31%. For the sample mean to be less than 176 pounds, it was about 2%. So it makes a huge difference in the probabilities.